All right, chapter 2, introduction to proof techniques. There are 3 types of techniques, proving techniques. One is direct proof, contradiction, and induction. Okay, we start with direct proof. Okay, look at this question, this example. Question example 1. The sum of any two even integers is even. You have to prove the statement. You have to prove this statement by using direct proof. So the sum of any two even integers is even. First, you have to make an assumption. You assume two even integers. So we cannot assume by using numbers. We have to use variables. So we assume two even integers. Assume x and y are two even integers. Okay, we assume x and y. You can use any variable. You can a, b, d, e, any variables. Okay, so here I use x and y. Assume x and y are two even integers, and then step 2, you have to define. When you make an assumption, then you have to define, because your computer doesn't know what is even integer. Okay. Define x and y. Okay, how to define even integer? X equals to 2a. So this is how we define even integer. 2a. Why 2a? So any numbers or any integers, when you substitute into a, you will get even number. Let's say, okay, I want to substitute a by 9. So x equals to 2 times 9 equals to 18. 18 is an even integer. A equals to 4. So x will be 8. So 8 is an even integer. So whatever values you enter into A, you will get even number. So this is how we define even number. And then after we define x, we have to define y. Because x and y, right? So x and y are two even integers. So define y. Y, we define y equals to 2b. Why 2? Because even number. Okay, why I use b? Here I use a and here I use b, because x and y are two different numbers. Right? So we cannot use the same variable. If let's say I put here a, I will get the same value for x and y. Right? So I put different variable a and b. And then after we define x and y, we have to state here for some integers a and b. Okay, why I have to say for some integers a and b? Only integers can be substituted into a and b. Right? And then step 3, we prove. So to prove, we look at the step. Any two even integers, so you have to add up the numbers, right? The sum. So prove x plus y. Okay, the sum. So we have to add up x and y. X plus y equals to 2a plus 2b. Okay, x we define as 2a and y we define as 2b. So 2a equals to 2b. And then we want to simplify the equation. We factorize 2. In the bracket will be a plus b. And then again, let k, we use new variable to simplify the equation. Let k equals to a plus b. So it will be x plus y equals to 2k. 2k is an even number, right? 2k. So whatever value and substitute into k will get even integers. So satisfies the statement, right? Satisfies this statement. Because in this statement, the sum of any two even integers is even. So now we have proved that when we add x and y, we get even integer. Okay, when you enter new variables, again you have to state for some integers k. Only integers can be substituted into k. Then a short conclusion, you can say here 2k satisfies of being an even integer. Can you understand?
Yes, madam.
All right, good. So we move to the next example. Okay, look at this example. The sum of any two rational numbers is rational. What is rational number? Rational number is a fraction number. The sum, again, the sum of any two rational number is rational. So now we have to assume two rational numbers. Assume x and y are two rational numbers. Okay, and then you have to define x and y. Okay, so define here x equals to, how to define rational number? A over b, right? And y equal to c over d. You can use any variables, So, and then, okay, now we already insert new variables, right? A, B, C, D. So we have to say here for some integers A, B, C, and D with B and D not equals to 0. So B and D cannot be 0 because fraction number denominator cannot be 0. If I have 2 over 0, it will be maths error, right? 3 over 0, maths error. So here you have to put the condition there. B and D cannot be 0. So only other integers other than 0 can insert into B and D but not 0. Right? Okay, now third step, we have to prove. You prove, how to prove x plus y, right? So A over B plus C over D. Solve this, it will be AD plus BC over BD. And then you can simplify this by let what k equals to AD plus BC, and then let M equals to BD. Then your equation will be x plus y equals to k over M. So k over M is a fraction number. K over M is a fraction number. Then here you can say for some integers k and m with m not equals to, is not equal to 0. Again m, the denominator cannot be 0. So here you can write short conclusion k over m satisfies of being a rational number. Okay? Okay, are you okay, guys?
Okay, madam.
Okay, madam.
All right. Next. Okay, if x and y are two odd numbers, then x plus y is even number. So here it's already stated variable x and y. So we use x and y are two odd numbers. And then x plus y is even number. So we have to prove this. Suppose or assume x and y are two odd numbers. And then step 2, you define x and y. Define x equals to, okay, how to define odd number? 2a plus 1. To define even number, 2a, 2b, 2c, okay? But for odd number, you have to 2a plus 1. Or any variables are 2x plus 2b plus 1, 2c plus 1, okay? For odd number. So whatever value you enter a, you substitute into a, you will get odd number. Okay, this is for x and then y. Y also odd number. So y equal to 2b plus 1. For some integers a and a and b. Then proof. We want to prove. So we have to prove this, x plus y is even number. So x plus y equals to, okay, x we define as 2a plus 1. Put the bracket. B. For y, we define 2b plus 1. Expand the bracket, we get 2a plus 2b plus 2. So we can factorize this to, in the bracket will be a plus b plus 1. And then let k equals to a plus b plus 1. So your equation will be x plus y equals to 2k. Okay, 2k is an even number. So it satisfies the statement x plus y is even number. So for some integers k. So you can see here 2k satisfies of being an even number. So, okay, all of you?
Okay, madam.
Okay.
All right, good.
Okay.
We have finished direct proof. Okay, now we go to contradiction. Okay, for contradiction, okay, I go to the example. Go straight to the example. All right, look here. There is no greatest integer. Okay, the statement is there is no greatest integer. You have to prove this statement. Okay. Yeah, we have no great. Can you define what is the greatest integer? Can you define what is the largest number? What is the greatest number? Or greatest integer? We can't define, right? We cannot define. Why? Because if you say infinity is the largest or the greatest number, we have infinity plus 1. Infinity plus 1 is greater than infinity. If we say infinity plus 1 is the greatest, we have infinity plus 1 plus 1. So we can't define what is the greatest integer. So now we have this statement, there is no greatest integer. So how to prove this? Okay, by using contradiction. Now we go to the second method, a second proving method. That is a contradiction. Okay, now we want to prove this statement by using contradiction. In contradiction, you have to make an assumption, but the assumption that you make is a contra assumption. Contra with the statement. In your assumption, you have to make contra statement. Contra statement. Then you have to prove your assumption is false. Then only you can say the statement is true. Do you get me? Okay, look at this example. There is no greatest integer. Okay, this is our assumption. This is the assumption. Step 1. Assume that n is the greatest integer. Can you see? This is the opposite statement or the contrast statement with this question lah. There is no in this question there is no greatest integer, but in our statement we assume that n is the greatest integer. N, we use n here. Assume that n is the greatest integer. Okay, now we want to prove that our statement, our assumption is wrong. This is our assumption. We have to prove that our assumption is wrong. So how to prove? Here, look here. Okay, if we say n is the greatest integer, after n we have n plus 1. N plus 1 is also an integer, but n plus 1 is greater than 1. So n plus 1 is an integer, but then n plus 1 is greater than n. So this is contradict with the assumption. In our assumption, we say n is the greatest integer. If n is the greatest integer, should be no numbers after n, right? If n is the greatest, but here we have n plus 1. N plus 1 is greater than n. So we have proved that our assumption is wrong, is false. So the statement is true. Can you understand? Okay, now look at this example. Show that or prove that 29 is a prime number. Okay, we want to prove 29 is a prime number, but we want to use contra method. Contradiction. Contradiction. First, we have to assume contra statement. We make a contra assumption. Contra assumption. So what is our contra assumption? In the statement, 29 is a prime number. So in our assumption will be 29 is not a prime number. Can you understand? Okay, 29 is not a prime number. So when we say 29 is not a prime number, we know that prime number is a number that can be divided by 1 and itself. So now we say 29 is not a prime number. If 29 is not a prime number, there must be other numbers. When we multiply, we get 29. Other than 1 and 29 lah. Beside 1 and 29, there must be other numbers. When we multiply, we get 29. Did you get me? For example, like 18. Yeah, I show you 18. 18 is not a prime number. So 18, 1 and multiply by 18, yes, we get 18. Right. But other than 1 and 18, there are other numbers. 2 multiplied by 9. What else? 6 multiplied by 3. There are other numbers. When we multiply, we get 18. 17. 17 is a prime number. Everyone knows that 17 is a prime number. So only 1 multiplied by 17, we will get 17. Okay. Okay, now 29. Now our case is 29. It's not a prime number. So for this 29, there must be other numbers. When we multiply, we want to prove. Our assumption is false. But we have to show 29. Let's say I use R multiplied by S. So what are R and S? Beside 1 and 29, we cannot use 1 and 29. Beside 1 and 29. So here we can list all the possibilities value. Let's say 2, 3. Why I start from 2? Because prime number start from number 2. And we cannot use 1 and 29. So 2, 3, 4, 5. We don't take 6. 6. We don't take 6. Why? We stop at 5 because 6 times 5 is 30. 30 already exceed 29. So we stop at 5. So among these four numbers, can you multiply, you get 29? Tak boleh, sorry, cannot, right? There is no numbers when we multiply, we get 29. So we have proved that our assumption is false. Meaning that 29 is a prime number. Okay? Can I proceed?
Yes, madam.
Okay, look at this example. Prove that if n square is an even integer, so is n, means that n square is even and also even. So they are like two statements here. This is the first statement, n square is an even. And then there is a second statement here, so is n, means n is also even, right? So if you have these two statements in one question, you have to prove this. We take the second statement here, the second statement as our contra assumption. And for this first statement, we just follow. For the second statement, we take our contra assumption. So we want to prove this. Here, this is the first statement and this is second statement. So we take this as our contra assumption. So in this statement, n is also n must be even lah, n also even. So in our assumption, we say that n is odd integer. N is odd. Okay, and then n square is an even integer. Okay, and then we can define this. We define n equals to, here we state odd integer, right? So n equal to 2a plus 1. So n square also, we can also define this n square. So this n square equals to 2b plus, oh sorry, even even, so 2b. Okay. After we define, we have to prove. Okay, how to prove? When we want to prove, we go back to the question here. Prove that if n square is an even integer, so is n. So when we square, we have to prove that when we square this n, we will get even integer. So n, we square this n, we square our n. Then when we square our n, this also we have to square, 2a plus 1. So expand the bracket, 2a plus 1. 2a plus 1, it will be 4a square plus 4a plus 1. I hope you know how to expand this. And then, to simplify the equation, we can factorize. We can factorize this 2a square plus 2a plus 1. We only factorize this part. 2 in the bracket 2a square plus 2a and then plus 1. Then let k equals to 2a square plus 2a. So our equation n square equals to 2k plus 1. 2k plus 1 is an odd number. But in our assumption, we say that n square is an even integer. So this is contradict with the assumption lah. In our assumption, n square equal to 2b, right? It's different with 2b. We can say here 2k plus 1 is an odd integer, which is contradict with the assumption. With the assumption and then with the assumption. So the statement or the above statement is true. Boleh faham? Can you understand?
Can you repeat, madam?
Yes.
All right. We go to the next example. If x and y are two even numbers, their sum is always even. X and y are two even numbers, their sum is always even. Okay, here we have first statement. X and y are two even numbers, their sum is always even. This is the second statement. So this is the first statement and this is the second statement. Okay. First, we have to make an assumption, right? So this assumption will be our contra assumption, and this one we just follow. So we can say here x and y are two even integers. Another assumption, x plus y, their sum, x plus y is odd, is an odd integer. Okay, and then we can define this x and y. Define x equal to 2a and y equals to 2b. And then also we can define x plus y. So x plus y equals to 2c plus 1. Why 2c plus 1? Because in our assumption, we assume as odd integer. So for some integers a, b, and c. Okay, only integers can be substituted into a, b, and c. Okay, then third step, we prove. Okay, when we want to prove, we'll go back to the statement, the question. X and y are two even numbers, their sum is always even. So we have to prove that x plus y. So our x and y here we assume as we define as 2a and 2b, right? 2a plus 2b. We can factorize this will be me, and then let k equals to a plus b. So x plus y equals to 2k. 2k is an even integer. 2k, because whatever value you insert into k, you will get even number. So 2k is not odd integer. But in our assumption, x plus y is an odd integer here. So 2k is not equal to 2c plus 1 here. This is our definition here. 2c plus 1. Then we have proved that our assumption is false and the statement is true. So this is contradiction. Okay. We have done 2 methods of proving. Now can we go to induction? The third method. All right. Induction. By using the principle of mathematics induction, okay, this is mathematics induction means induction method. Induction, mathematics induction prove that 1 plus 2 plus 3 plus n equals to n plus 1 over 2. Sorry, n multiply n times n plus 1 over 2. So for this induction method, there are 3 steps that you have to show. You cannot skip any step. If you skip one step, you will get wrong lah. You will get less mark. So here I 1 plus 2 plus 3 plus n equals to n plus 1 over 2. First step is n equals to 1. So this is the first step. N equals to 1, you substitute 1 into n. So 1 equals to 1, 1 plus 1 over 2. So 1 equals to 1, 1 plus 1 is 2 over 2. You can simplify this, you will get 1 equals to 1. So it's already proven. We have proved that the left hand side and the right hand side are equal. Okay, next step is n equals to k. Okay, n equals to k. This is not x, this is k. N equals to k. Okay, in the second step, you just substitute. But you have to write the whole equation. So 1 plus 2 plus 3 plus k equals to k plus 1 over 2. Okay, k equals to k plus 1 over 2. That's all. You don't have to do anything. Just substitute k into n. But you have to write the whole equation. Okay, third step, n equals to k plus 1. Okay, in the third step, n equals to k plus 1. You substitute k plus 1 into n. So it will be 1 plus 2 plus 3 plus n. Okay, I put here k plus 1. I put the bracket. If you don't put the bracket, you will tend to make mistake. If I don't put the bracket, it will be k plus 1. It will different numbers. It will look like 1 plus 2 plus 3 plus k plus 1. But actually, this k plus 1 is one number. That's why I put the bracket. So k plus 1 equals to, okay, here. Oh, look at the question here. So k plus 1 in the bracket k plus 1 over 2. Okay, in this bracket we can solve this first. So it will be 1 plus 2 plus 3 plus k plus 1 equals to k plus 1. Here will be k plus 2 over 2. Okay, until this line, can you understand?
Yes, sir.
Okay, good.
Medium. Can.
Okay. All right, now look at this. I have 1 plus 2 plus 3 plus nanti k plus 1. Actually, this is the first number. This equation means that this is the first number and this is the second number and this is the third number. Until here, this is the k plus 1 number. You get me? Actually, this is the summation from the first number to the k plus 1 number. The total is on this right hand side, k plus 1 times k plus 2 over 2. Okay, so summation from the first to the k plus 1 number, the total is this one, k plus 1 times k plus 2 over 2. We want to prove, is it true? Is it true that this summation equal to k plus 1 times k plus 2 over 2? So how to prove now? Our task here, we have to prove on this left hand side, on this part. We have to prove this, make sure we get the same total as this. The same equation as this. Okay, now from the first to the kth plus 1. Before kth plus 1 number, it will be kth number right here. Do you get me? Before kth plus 1, it must be kth number. Okay, summation from the first to the kth number. The total is in the second step. Actually, in this second step, shows you summation from the first number, second number, third number until kth number. The total is k times k plus 1 over 2. So we already have the total in the second step. We just put here. So summation from the first to the kth number, the total is k plus 1 over 2, and then plus this number. Plus this number. This is the kth plus 1 number. This is the kth plus 1 number. So you have to add up this total plus kth plus 1 number. So plus k plus 1. Put the bracket. Okay, now we have to solve this part, these two. This is over 1, right? So to the fraction number, you have to make the denominator same, right? Same denominator, then you can solve. So here multiply by 2, here multiply by 2. So it will be k plus 1 plus 2 times k plus 1 over 2. Okay, until this line, can you understand?
Yes, madam.
Right. So from this, you can, if you look here, you can just factorize, no need to expand. Don't expand. You can expand if you want, but it will take time. Okay. So you just factorize, will get k plus 1, k plus 2 over 2. And now we have proved that this left hand side is equal to this right hand side. K plus 1, k plus 2 over 2. So we prove it. Okay, here how I factorize. If you look here, k plus 1, this k plus 1, assume, let's say this is A and this is A. So you will get ka plus 2a over 2. So I just factorize A. So in the bracket will be k plus 2. So A, what is A? A is k plus 1, right? We write back k plus 1 times k plus 2. This is how I get this numerator. K plus 1 times k plus 2 over 2. Any questions?
Madam,
Hmm?
saya tak faham yang final answer.
This line,
Yes. How to get it?
factorize. This line you understand or not? This line. At this line, can you understand? Macam saya dapat ni, how do I get this k plus 1 plus 2 times k plus 1?
Ya, itu paham.
Okay. Okay, from here, how do I get this? I just factorize. Like I said just now, I just factorize k plus 1. Here I got k plus 1 kan? I assume this k plus 1 is A. So when I assume this A, it will be KA plus 2A here. So I factorize A, in the bracket will be K plus 2. So this K plus A, we write back, what is A? A is K plus 1 kan? So we write back this K plus 1 times K plus 2. So this is how I get this. K plus 1 times K plus 2 over 2. You get me?
Okay, madam.
So we go to the next example. If you look at this example, 1 over 3 multiplied by 5, 3 times 5. 1 over 3 times 5 plus 1 over 5 times 7 plus 1 over 7 times 9 plus 1 over 2n plus 1 times 2n plus 3 equals to n over 3 times 2n plus 3. So first step is n equals to 1. Substitute 1 into n, it will be 1 over 2 times 1 plus 1. Close the bracket. Second bracket, 2 times 1 plus 3. Close the bracket. Equals to 1 equals over 3 times 2 times 1 plus 3. So it will be 1 over, so 2 times 1, 2 plus 1 is 3, right? Here 2 times 1 is 2 plus 3 is 5. Here 3, 2 plus 3 is 5. We get 1 over 15 equals to 1 over 15. So we have proved that both sides are same. And then second step is n equals to k. Substitute k into n. So our equation will be 3 times 5 plus 1 over 5 times 7 plus 1 over 7 times 9 plus 1 over 2k plus 1, 2k plus 3 equals to k, 3, 2k plus 3. That's all. Second step. And then n equals to k plus 1. Okay, k plus 1 substitute into n, I write the whole equation plus 1 over 5 times 7 plus 1 over 7 times 9 plus 1 over, okay, this one is quite long. So I show you here. We have 2n plus 1, right? For the denominator, 2n plus 3. We substitute k plus 1 into n, it will be 2 times k plus 1 plus 1 here. Okay, here 2 times k plus 1 plus 3. Expand the bracket, it will be 2k plus 2 plus 1. Here 2k plus 2 plus 3. So 2k plus 3 in the first bracket, second bracket 2k plus 5. So 2k plus 5. 2k plus 3 times 2k plus 5. Yeah, I just write here 2k plus 3 and then 2k plus 5 equals to n. So this is k plus 1 over 3 k, 2n plus 3, 2n, n substitute by k plus 1 will be 2 plus 2k plus 5. Okay, until this line, can you understand?
Yes, madam.
Right. So now look at this equation. Okay, this is the first number. Actually, this is the first number. This is the second number, and this is the third number, and this is the kth plus 1 number. Summation all these numbers equal to this. K plus 1 over 3 times 2k plus 5. Okay, before k plus 1 number, it must be here. K number. Before k plus 1. Summation from the first to the kth number. The total is in the second step. So we can just take this equation. K will be k over 3 times 2k plus 3. Okay, this comes from second step, plus this. We have to plus with this k plus 1 number. So k plus 1 number is 1 over 2k plus 3, 2k plus 5. Can you understand until here? Okay, now we want to solve this. We want to solve these two and to get the same value as on the right hand side. Yeah. Okay, look at this fraction number. Look at the denominator. Here we have 3, 2k plus 3, and this side we have no 3, so we have to multiply by 3, multiply by 3. And on this side, we multiply by 2k plus 5. Okay, so it will be k times 2k plus 5 plus 3. 1 times 3 is 3 over 3, 2k plus 3 times 2k plus 5. And then, what can we do? We expand this. We can expand this. It will be 2k square plus 5k plus 3 over 3, 2k plus 3, 2k plus 5. Then we can factorize this. This is quadratic equation. Okay, this quadratic equation we can factorize. You can factorize manually or you can use calculator. But when you use calculator, you will get the root number. Then you have to convert back. So how to factorize manually? I bet you already know. You learn this in school. Yeah, I show you here. We have 2k square plus 5k plus 3. I want to factorize this. So 2k square, 2k multiplied by k will be 2k square. 3 times 1 equals to 3. Then we check this equation. 2k times 1 is 2k. K times 3 is 3k. And then we plus these 2. 3 plus 2 equal to 5k. So 5k is equal to this middle value here, 5k. And then now our factorization is correct. So we can write the factors. How to write the factors? We write it with horizontally, 2k plus 3. So it will be 2k plus 3 and k plus 1 over 3, 2k plus 3, 2k plus 5. Then, okay, if you look at this, you can simplify this. 2k plus 3 and 2k plus 3, we can just cancel out. So our equation will be k plus 1 here over 3 times 2k plus 5 is equal to this. Where is our is equal we have to this our right hand side, k plus 1 over 3 times 2k plus 5. So we have proof. Can you understand?
Can, madam.
Any questions? All right, if you have no questions, I will stop here. I will continue 3 more examples in tutorial class. Is it okay?
Yes.
Okay.
All right.
Boleh, madam.
So next week on Thursday, we will have tutorial. So before we do the tutorial, I will show you another 3 more examples, and then you do your tutorial. So if you have if you have any questions or any part that you don't understand, you can ask me. Let me know, right?
Okay, madam.
Okay, madam.
Okay, good. LO3, please scan your attendance.
Madam. Madam.
Yeah. Oh, you want me to key in your name?
No, madam.
Yeah.
Tapi pagi tadi kan kita orang terlibat dengan program pagi tadi jadi attendance. Tak sempat.
You apply leave?
Boleh? Saya letak screenshot maklumat ke madam atau madam nak?
Boleh. Anything.
Okay, madam.
LO3 done. LO4?
Thank you, madam.
All right.
Thank you, madam.
Okay.
Thank you, madam.
Madam, Manuel.
Nama?
Siti Nur Aisyah binti Anwar.
Siti Nur Aisyah. Alright.
Okay, thank you, madam.
Thank you, madam.
Welcome.
Madam.
Yes? Ya.
Saya 03 tadi tak sempat nak scan.
Kejap.
Madam,
Ya.
Raja Nur Amirah.
Raja.
Ha. Thank you.
Thank you, madam.
Alright, welcome.
Madam, Miss
Ya.
Shakira.
Siapa? Shakira. Ni.
Ya, madam. Betul, madam. Thank you, madam.
Alright.
Madam, Nur Hazwan.